Thanks a lot for coming. Today we have Akash Kumar from EPFL, and he will be talking about random walks and forbidden minors.
Okay. So thanks for having me. Thanks, Jungkyung. So as Jungkyung mentioned, today I'd be telling you about random walks and how random walks help make progress on algorithmic problems for planar graphs. So I'd be talking about works that I did jointly with Seshadhri at University of California, Santa Cruz, and Seshadhri-Stolman, who is at Katana Labs. Okay, so let's get started. So to begin with, I will tell you about the object that is like the most relevant member of today's cast. So I have a cast of characters, and the most important member in my cast are planar graphs. So what are planar graphs? So these are graphs that you can draw on the two-dimensional plane without its edges hitting each other. So the graph pictured on this slide, the complete graph on 4 vertices, is a planar graph. It is just that I have drawn it badly. You can fix this drawing like so, and it confirms that this graph is indeed planar. So if you think about it, like if you take complete graphs on like really lots and lots of vertices, they have too many edges. So perhaps you are persuading the edges to hit each other, and you will, as a result, get a non-planar graph. This intuition is absolutely spot on. And turns out that you get non-planar graphs for fairly small graphs. So for example, the two graphs shown here on this slide are non-planar. They are famously non-planar. So on the left, you have the complete graph on 5 vertices. On the right, you have the complete bipartite graph with 3 vertices on each side. So if you were to ask that, hey, can I characterize planarity? Is there an if and only if theorem that characterizes when a graph is planar? The answer is of course yes, and the solution dates back to 1930s. And thanks to a solution developed by Krotkowski and Wagner, it turns out that a graph is planar if and only if it does not contain, for some appropriate meaning of containment, it does not contain the two graphs shown here on this slide. Okay, this notion of containment has a name. It goes by the name of graph minors. Okay, and like this notion is not too bad. So let's quickly see what graph minors are. So we say that a graph H is the minor of a graph G, or a graph G contains a graph H as a minor if you can obtain a copy of graph H by messing around with a copy of graph G. So how do you mess around? So you're allowed to delete edges inside the graph G, and you're allowed to contract edges inside the graph G. So you take an edge and you collapse the edge into a single mega vertex, and like that's the contraction operation. And if there is a sequence of deletions followed by contractions, after which you obtain a copy of H starting from a copy of G, we say that the graph G contains the graph H as a minor. Okay, let's make sure we understand this notion through an example. So I claim that here on this slide, the graph on the right contains a complete graph on 5 vertices as a minor. So how can you verify this? So you notice that if you were to shrink these 5 red islands into one big single mega vertex, you will have vertex join paths shown in blue here running between every pair of islands. So this confirms that the graph on the right indeed contains a K5 minor. Okay, so if this is your first time looking at the definition of a graph minor, you might be wondering that, hey, why should I care about this notion? So here is a joke answer. So in a series of 23 papers, Robertson and Seymour showed what is called the graph minor theorem. It's a very powerful theorem which illuminated a lot of landscape in structural graph theory, which also helped us in making progress on algorithmic questions about graphs. So like a more serious answer would be the following, that you should care about graph minors because they help you answer like a lot of interesting questions. For example, they help you answer embeddability questions. So remember that question that Krotkowski and Wagner answered about when can you embed or draw a graph in the two-dimensional plane without its edges hitting each other? You can also ask a similar question about when can you draw graphs on more exotic surfaces. For example, like this coffee cup, when can you like draw graphs on this coffee cup without its edges hitting each other? So that can also be answered via the theory of graph minors. And then it also turns out that a truckload of interesting graph properties end up being minor closed. For example, consider the property of your graph being acyclic. If your graph is acyclic, remember the notion of minors is a notion of containment, right? So if your graph is acyclic, then everything that it contains should also be acyclic. Namely, all of its minors should also be acyclic. And interestingly enough, it happens that a lot of interesting graph properties exhibit this behavior, that they are minor closed. Okay. And like finally, thanks to connections to like a bunch of coloring problems and things like bounded tree width, notions of bounded tree width, the entire area of like fixed parameter tractability, etc. I mean, graph minors are indeed an important notion, and they are here to stay. Like, by the way, feel free to stop me if you have any questions. Okay. So,
may I ask a question actually here?
Yes, please.
You said that graph minors are helpful for embeddability questions, and I saw a concept like embedding graphs on not sphere but other topological spaces like a torus, for instance, or other topological space of higher genus.
Okay.
Is it also helpful there? Like, are they also useful for embedding graphs on other topological surfaces?
Yes. So the notion of graph minors is relevant there as well. The thing is that what you can show is that there is a finite list. So fix a surface first with some genus and like the surface is a donut or something. And now what you can show is that like once you fix a surface, then there is a finite list of forbidden minors, such that if your graph does not contain like any graph from this list as a minor, then your graph can be drawn on that surface without any edges hitting each other. Okay, this list has a finite size. We do not know what that list is.
Oh, okay. Actually, that's a powerful, then let's say, theorem or fact.
Yeah. So it leads to like, I mean, just as an interesting anecdote, it leads to this interesting issue. So you know that if I fix the surface, then you have a polynomial time algorithm that can decide whether a graph can be embedded on that surface or not. Unfortunately, you do not know what this algorithm is because you do not know what that annoying list of forbidden minors is. Okay, so you know that the problem is in P, but you do not know the algorithm. So yeah.
Okay, I get it. Thank you very much.
Okay. So now let me move on to the first part of the talk. The first part of the talk considers the following question, that how it illuminates the following interesting thing that we like discovered a while back, that I want to tell you the story of how random walks led to algorithms for finding minors in graphs that are sufficiently not planar. Okay, so now let me like unpack what sufficiently not planar means through the framework of property testing. So the idea is going to be the following. So in the rest of this talk, every single graph that I'm talking about, they are always going to be bounded degree graphs. So this big white rectangle here, it denotes the universe of all bounded degree graphs. Okay, of like, let's say degree at most 10, some constant d. Okay. And this yellow part of the egg over here, it denotes an interesting subset. It's the subset of all planar graphs of bounded degree, maximum degree d. Okay. And there are graphs that sit outside the white region of the egg. I think of these graphs as being blatantly not planar, as being like super non-planar. Okay, let's just try to like formalize this a bit more. So my graph is a bounded degree graph. So how is it given to you? It's given to you as the adjacency list. So I will answer the following queries happily for you. You ask for vertex number I give you vertex number I. You ask for fifth neighbor of vertex number I give you the fifth neighbor of vertex number I, thanks to the adjacency list. So this representation allows you to explore the graph locally by crawling along its edges. Okay, so you can like sample a whole bunch of random initial vertices, and you can do breadth first searches, depth first searches, or you can just do plain old random walks. Okay, so that's how we explore the graph. And now let me like describe what this epsilon really means here. Okay, so I define for you a notion of distance between a pair of graphs, of bounded degree graphs. And this notion of distance is the following. It's just going to be a fractional symmetric difference between the adjacency lists of your graphs. So you have a graph G and a graph G prime. You look at the symmetric difference between their edge set, and you divide it by n times the degree bound, n times d. Okay, so in particular, like graphs that come from stuff outside the egg white, okay, you must destroy an epsilon fraction of edges in such graphs to get a planar graph. Okay, so any questions about the notion of distance? Okay, So I'll move on. And now I want to introduce the two problems that I'm interested in the first part of this talk. So the first problem is the so-called one-sided testing. So here what I want you to do is I want you to develop an algorithm for me that always accepts planar graphs. It accepts planar graphs with probability 1. And this algorithm should have a good chance of rejecting graphs that come from outside the egg white. It should reject a graph that comes from outside egg white with probability at least 2/3. Okay. So notice that since I insist that your algorithm should always accept planar graphs, whenever your algorithm rejects a graph, it should have a certificate of rejection in its hand. So it should be able to tell you that I rejected this graph and here's a certificate Y. So any questions about the one-sided variant? I'll pause for half a minute. Okay, so I hope that the problem statement is clear. If it's not, feel free to stop me. Now we'll introduce the two-sided variant of this question. This two-sided variant just says the following, that hey, now you are no longer required to always accept planar graphs. You can accept them with probability at least 2/3. And the rejection criteria, it remains the same. Okay. So these are the two variants that I wanted to talk about. And having presented these variants, now I'd like to tell you a little bit of history on this problem. Okay. So what was known before. So back in 2008, Benjamin, Schramm, and Shapira presented an algorithm that ran in time triply exponential in the degree over epsilon. No dependence on n. Okay. That's quite remarkable that the running time of the algorithm has no dependence on the number of vertices in your graph. It depends only on the proximity parameter epsilon. Okay, back in 2008 itself, Benjamin, Schramm, and Shapira conjectured that you can solve this problem in time polynomial in 1 over epsilon. And they also conjectured that you could solve the one-sided variant in time roughly root n times some polylog terms. Okay. Then in 2010, Hasidim, Kellner, Newend, and Onak presented algorithms that ran in time singly exponential in degree over epsilon. Okay, and their methods were refined by Levy and Ron in 2015. Who derived algorithms that could run in time quasi-polynomial in 1 over epsilon. So this is what was known about the two-sided variant of this question. For the one-sided variant, we had a different story. For the one-sided variant, for the special case of cycle minors, Shumai, Goldreich, Ron, Seshadhri, Shapira, and Soler, so there should be one more S here, showed in 2014, they presented in 2014 an algorithm that could decide whether your graph is cycle minor free for some fixed R. So whether it's C5 minor free or whether it's far from being C5 minor free. Okay, so they presented root and time algorithms, roughly root and time algorithms for this problem. And in this paper, they also showed a matching lower bound, a root and lower bound for this problem. Okay. And then in 2017, Fichtenberger, Levy, Vasudev, and Wachtel presented an algorithm that ran in time into the 2/3. And it could find complete bipartite minors with 2 vertices on the left. Okay, in graphs that are sufficiently far from such minors. Okay, so what I did in joint work with Seshadhri and Stolman is that I resolved essentially both of these conjectures. So we resolved the two-sided variant completely. We gave a algorithm that runs in time polynomial in 1 over epsilon as conjectured by Benjamin, Schramm, and Shapira. For the one-sided variant, we gave an algorithm that runs in time roughly is root n. It just has sum into the little of 1 slack. Okay, so these are the two theorems that I would like to tell you about. Any questions so far? Okay, so I'll move on. And now let me tell you the statement of the main theorem. Okay, so for the one-sided land. So this theorem tells you the following, that essentially there is an algorithm that does the job. So you have an algorithm which on input, a bounded degree graph that is sufficiently not planar. What this algorithm does is that it runs in roughly root n time and it finds for you a K5 or a K33 minor hiding inside this graph with good probability, with probability at least 2/3. And here O star hides into the little o of 1 terms. Okay. Like, and also like our algorithms, they extend for like all minor free graph classes, but I will only talk about planar graphs because like planar graphs are kind of nice. Okay. And now let me also tell you our theorem for the two-sided variant. For the two-sided variant, we have the following result. That again, essentially the same statement. You have an algorithm that does the job. So you have an algorithm which on input a bounded degree graph G. What it does is that it runs in time polynomial in 1 over epsilon, and it outputs the correct verdict. It outputs the correct yes/no verdict. So it says yes if your graph is planar, and it says no if your graph is sufficiently not planar. And the verdict is correct with probability at least 2/3. Yes, please. Any questions? You can still hear me, right? I just want to make sure.
Yes, we do hear you.
Okay, good.
Yeah,
good. Okay, so like these are the two theorems that like I'd like to tell you about, and now I want to like give you a generic recipe to attack such property testing questions on bounded degree graphs. So in my opinion, like this recipe, which was formulated by Goldreich and Ron, is like significantly more important, is much more important than any of our results. So like, let me tell you what this recipe is. And so there is this entire recipe that allows you to attack like property testing questions. And I think that this is cool. Okay, like, but before I tell you this recipe, I need to like revisit the notion of expanders. I need to tell you what expanders are. So let's just quickly recap what expanders are. Okay. So like my graphs are always bounded degree, so I might as well consider regular graphs, deregular graphs. So I will just add enough self loops if the graph is not like already deregular. Okay. So expanders, they're just a notion of connectivity. So I have a 3 regular graphs. Think of the case where D is exactly 3. I have a 3 regular graph and I'm telling you it's very well connected. So you might be surprised that, hey, a 3 regular graph is definitely not well connected because I take vertex number 1 and I delete all 3 edges falling on vertex number 1. So in what sense is this graph well connected? So it's well connected in the following sense that like take any small subset of vertices S. So S contains less than half the vertices. And like the notion of expanders essentially says the following, that it's difficult to disconnect S from the rest of the graph in the following sense. It's a deregular graph. So the total number of edges falling on S is D times the size of S. And the number of edges that go between S and the complement of S is large. It's at least an alpha fraction of D times S. Okay, so like essentially we define this quantity expansion of S. It's the following ratio. It's the number of edges going from S to S complement, the edges that you must delete to disconnect S from the rest, divided by total number of edges incident on S. Okay, and like this ratio is large for all small sides, for all sides of size at most n over 2. So if this ratio is at least alpha for every single smaller side, then I say that your graph is in fact an alpha expander. So for now, think of the case where this ratio alpha is at least a constant. Okay, now like let me quickly tell you a fun fact about such expander graphs. So that fun fact is that random walks mix quickly on expanders. So let's quickly recap what random walks are. So I give you like this graph and you're standing at a red vertex and you do the following process. So you go to a random neighbor of this red vertex and you keep on doing this for a while. And that's essentially all there is to a random walk. So like let's begin by taking like the graph that is like the best like supremely well connected graph, the complete graph. So in complete graph, if you start a random walk at let's say vertex number 1, in one step you are at a completely random vertex, right? So in expander graphs, random walks mix in one step. In complete graphs, like random walks mix in one step. In expanders, a similar phenomenon holds. Like so mixing just means that the distribution over the endpoints of a sufficiently long random walk is approximately the uniform distribution. So as we saw that in complete graphs, random walks mix in one step. In expanders, a similar phenomenon happens. So for example, if you let D denote the distribution over the endpoints after you do a logarithmic length walk in an expander graph, what you would notice is that this distribution D is almost the uniform distribution. It's very close in L1 to the uniform distribution. Okay, and like in fact, you can confirm that the 2 norm squared of this distribution would be like very close to 1 over n, and 2 norm squared cannot shrink to a value any smaller than 1 over n. Okay, I mean that's just a simple proof followed by Cauchy-Schwarz. Okay, so with these facts out of the way, I can tell you the Goldreich-Ron recipe. So the Goldreich-Ron recipe tells you that you should do the following, that first, you should restrict your attention to expanders. So you want to solve a probabilistic testing question on bounded degree graphs, restrict your attention to expanders. So focus on the case where the yes instance is an expander and where the far instance is also an expander. So like on both sides, you are given expanders. So suppose you are able to solve this. Now Goldreich and Ron suggest the following rule of thumb, that in the general case, you should try the following recipe, that you can perhaps break your graphs, break the vertex set of your graph into subsets, where all the subsets induce expanders of some possibly poor expansion, maybe 1 over polylog expansion. But now, since you have a black belt in testing whatever property you wanted for expanders, what you could essentially do is that you could pretend that, for example, this piece is an expanding piece, and you use your expertise in testing properties over expanders to test the property over this subset, and hopefully that allows you to test the property in general graphs. Okay, so that's the Goldreich-Ron recipe. That first test on expanders, then exploit some decompositions, and maybe that helps you out. Okay, and that's remarkable that this recipe allowed people to test such a wide variety of properties. But now this is good for us because we have a hammer, the Goldreich-Ron hammer, and we have a nail, the problem that we want to solve, minor freeness. Okay, so let's get to work. Let's try to see if you can find minors inside expanders. Okay, so let's do that. So I'll find for you a K3 minor hiding inside an expander. So you start with 3 random vertices, the white vertex, the green vertex, and the black vertex as shown in this picture. And you perform square root n random walks of logarithmic length from all of these 3 sources. So you perform root n random walks from the white vertex, root n random walks from the green vertex, and root n random walks from the black vertex, all of logarithmic length. Since it's an expander, the length of the walk is logarithmic. The endpoints are uniformly random. They are uniformly random vertices. So you have root n random white endpoints, root n random green endpoints, and root n random black endpoints. By Birthday paradox, with constant probability, you have you get a white to green path, a white to black path, and a green to black path. So that's great. You were able to connect all the terminals. Okay, but is this enough to find minors? So it turns out that while in general this is not enough because remember there was some discussion of these paths being disjoint in the definition of graph minors. Right, but these paths are definitely not going to be disjoint because for example, if you perform root n random walks from the white vertex, at least 1/3 of these walks, root n over 3 of these walks, will use the same white neighbor. Okay, so these walks, they definitely intersect and intersect a lot. But turns out that in expanders, life is still fine. While in general, this is not enough, but in expanders, this still works out because you need to handle these intersections, but expanders are so well connected that you would be able to contract away these intersections. And you would be able to find a white to green path. So like the path shown over here. And you would be able to find a white to black path, the path shown over here, and a black to green path, and you can contract them all. And this way you can find a minor hiding inside expanders. But in general, this is quite difficult. So let me go over this more slowly. So what we want to do now is we want to adapt the machinery advocated by Goldreich and Ron for testing minor freeness. And as we observed, or as I hand waved, that in expander graphs, this machinery checks out. Everything checks out, and this is great. But what happens is that in arbitrary graphs, if you have to follow this recipe, stuff just gets complicated because what happens is that the intersection problem strikes back. And it's difficult to deal with the intersection problem. I'll tell you in more detail what exactly this intersection problem is. But the punchline is that the intersection problem really becomes a nightmare. Okay. And we were stuck here for quite a while. We were stuck here for more than 2 years. And finally, we realized that the way out of our dilemma was to generalize the expander analysis, was to break your graph into what you might call generalized expanders, and then exploit a decomposition into these generalized expanders. Okay. So I can tell you what the intersection problem is, but please feel free to interrupt me if you have any questions. Okay, so like I'll tell you what the intersection problem is in more detail. Let me just do a little recap. So what we discovered is that it is indeed easy to find minors hiding inside an expander graph. Okay. And like we were thinking that the following plan might work. So we were daydreaming that the following plan might work, which unfortunately does not. And the plan was that like if your graph is like epsilon far from being planar, hopefully we wanted to like break the vertex of this graph into pieces which induce expanders. Okay, like into pieces which induce expanders, and we hope that like random walks could be used to find minors inside such graphs. But like the following obstacle is the obstacle that you should be worried about, that the existing of the self-expander decomposition tools, they cannot promise very good expansion for like these pieces. The expansion that I can promise is merely 1 over polylog. And the external expansion might roughly be the same quantity, might be of the same order. So in these cases, what will happen is that the random walks, they will leave their home copy. So you wanted to find, let's say, a K5 minor or a K3 minor hiding inside this piece. But annoyingly enough, the random walks are going to behave in a very erratic way. They will just leave their home copy and they will never come back. Okay, so like that's the obstacle that we are worried about. Like again, like in more detail, if you want to simulate some naive decompositions that are known inside the literature, what happens is that like they do not give good guarantees of containing the random walks inside the copy. Okay, random walks just exit their home copy, and like that's the trouble that you have to fight with. So the existing decompositions shown in Aurora Barak-Storer in their 2015 paper, and the decompositions produced by Trevisan back in its 2005 paper, like all such decompositions, when you allow them to cut up to epsilon fraction of edges, the best internal conductance they can guarantee is merely 1 over polylog. And that is the essence of the obstacle that we have to fight against. Okay, so like now I would like to give you like the high level idea that allows you to fight this obstacle. But like again, I want to just check if there are any questions, like please go ahead.
Have you defined what conductance is?
So conductance and expansion, I use them interchangeably. So expansion is like just the number of edges going from S to S complement divided by the volume of the set. That's the expansion of a set S. Okay. Okay. So now like let me give you like the high level idea behind these generalized expanders that allow you to like make progress on this question. So the key idea is this, that remember in expanders, the key argument that we exploited was this birthday paradox. And the birthday paradox argument worked because random walks from every single vertex, they mixed rapidly. But you do not need random walks to mix well from every single vertex. Even if random walks mix rapidly from a mere handful into the 0.99 vertices, the birthday paradox argument will still go through. You would still be able to find minors inside such graphs. Okay, where random walks do not mix from every single source, they mix well only from into the 0.99 sources. Okay, they won't mix rapidly, like only from little o of n vertices. Even then, like the birthday paradox argument goes through. So we call such graphs generalized expanders, and we show a decomposition of your graph into generalized expanders. Remember, you cannot compute such a decomposition because you are allowed only sublinear time. So you have to simulate access to pieces of this generalized decomposition, like which we show how you can achieve. Okay, so like that's really going to be the key idea. And now I am ready to like tell you what our algorithm is. I just need 2 more ingredients, and like that I will set up on the next slide. Okay, like but again, like please feel free to like ask questions if you have any. Okay, so now like let me just set up the stage before I can present you like what our algorithm does. So let me just set up some notation real quick. So like you have a vertex V from which like you do L-length random walks. You know what this process is. You keep jumping to a random neighbor, and the notation that we use is PVL. It denotes the distribution over endpoints of an L-length walk that you do from the start vertex V. And you should think of the walk length as being n to the delta, n to the 0.01. Okay, And I call a vertex V leaky if the random walk from this vertex spreads very well. That is, if the 2 norm of this distribution PVL, it's small, it's at most L to the minus 10. I call such a vertex leaky. So like why are leaky vertices useful? So I mean, think about expander graphs. Every single vertex is leaky. Okay, because the 2 norm squared of a logarithmic length walk from the start vertex V for every single V, like it's 1 over n. The 2 norm squared is 1 over n, right? So the 2 norm squared shrinks. So such vertices, I call them leaky. So since in expanders, like the Berta paradox argument works well, you should have this intuition that if you have lots of leaky vertices, a similar behavior would carry over. Okay. And indeed, I am preaching to the choir here, because variants of leaky vertices were used in like works of Deb Somya, Jehun, Jinha, Mingi, and Hong in 22 to like solve a whole bunch of interesting questions. And like they showed how you can like obtain some interesting graph embedding results, like using some variants of like leaky vertices. And the key thing to note is that if your vertex is leaky, then an L length walk from such vertex, it can reach many possible destinations. It can reach a number of destinations that grows polynomial in the length of the walk. Okay, and indeed your intuition is that you have truckloads of leaky vertices, then just like in expanders, the Berta paradox argument was able to find a minor for you. If you have truckloads of leaky vertices, a similar analysis would carry over, and random walk should intuitively allow you to be able to find a minor. Okay, so now you might be interested in understanding that, hey, what if I do not have many leaky vertices? Like an overwhelming majority of the vertices, they are not leaky. What do I do then? Okay, in this case, you can show a claim of the following flavor, that suppose you have truckloads of non-leaky vertices. In particular, the white vertex here is non-leaky. That is, the 2 norm squared of L length walks from the white vertex is large. The 2 norm squared is, let's say, 0.01, just for the heck of it. Then what you can intuitively imagine is that there has got to be a sparse cut around this vertex, because the random walks are not spreading very well, right? I mean, they're kind of getting trapped and they do not cross over to the other side. So there has to be a sparse cut. Let's just quickly prove it. So what I will first argue is that there is a pair of successive steps. Among the first L steps, there are steps I and steps I plus 1, between which the walk definitely does not spread. So here is the set of the ith walk and like the levels of the I plus first walk. And what I'm claiming is that the 2 norm squared at the end of ith step is going to be larger, is going to be like very close to the 2 norm squared at the end of the ith step. Because if it did not happen, the 2 norm squared at every single step was at most 1 minus 10 over L times the 2 norm at the previous step. At the end of all the L steps, the 2 norm squared would be like roughly 1 minus 10 over L to the L, right? 1 minus 1 over 10L to the L, which is roughly to the negative 10. But I know that the 2 norm squared is very large. It's at least 0.01. So this cannot happen. There is therefore a pair of successive steps during which the walk refuses to spread out. Okay, so like this is going to be a like nice observation, and like recall that so it should be PVI here. That okay, right. So the 2 norm the probability vector at the next step equals the random walk matrix times the probability vector of the previous step. So if you just let X denote the probability vector at the ith step, you would have the following, that essentially this inequality, it could be read out in the following manner. This inequality is essentially telling you that the inner product of mx with mx is at least 1 minus 10 over L times the inner product of x with x. Okay, x is PVI. X is the probability vector of the ith step. It's just rewriting the inequality at this step. Okay. So M is a symmetric matrix. I assumed that my graph is deregular. M is a symmetric matrix. You could write this as like the inner product of M squared x with x. Okay, that's how you could write the left-hand side. Now, what is this saying? This is telling you that the adjacency matrix of M squared, like x is essentially an eigenvector of M squared with eigenvalue 1 minus 10 over N, right? X is essentially an eigenvector of M squared with eigenvalue 1 minus 10 over L. And the eigenvalues of M and the eigenvalues of M squared, they're related in a very nice way, that the eigenvalues of M squared are just squares of eigenvalues of M, right? So if the eigenvalue of M square is like 1 minus 10 over L lambda, the corresponding eigenvalue of m is the square root of lambda, which is again of the same order, 1 minus 10 over L, right? 1 minus 1 over L. So you have an eigenvalue of m that is fairly large, that is very close to 1. Okay. Spectral gap is fairly small. So if you just use Cheeger rounding, like a classic stuff from spectral arguments, what you will discover is that you have a cut with conductance at most 1 over square root L. Okay. So indeed, if your vertex is not leaky, you can discover a fairly sparse cut, a cut with fairly small sparsity around the start vertex, around this non-leaky vertex. Okay. So now I am ready to present my algorithm. Like again, like please feel free to interrupt me if you have any questions. Okay. So now I will like show my algorithm. So here is all our algorithm does. So like it's just a caricature of the algorithm. The actual algorithm requires you to add more bells and whistles to it. So like what you do is that the algorithm proceeds in a bunch of iterations. In a single iteration, you pick some initial vertex and you do not know whether your graph is leaky or non-leaky. So your algorithm has you just run subroutines for the non-leaky and leaky phase together. Both of these iterations will be run. The non-leaky case will do the following, that you will, suppose you want to find a K5 minor, you will launch 5 different random walks, which take you to 5 different destinations like V1 through V5. And then you just check tiny neighborhoods of V1 through V5 by performing more random walks. And you see if like these random walks, they reveal a minor. Remember, it's a non-leaky case. Okay, so an overwhelming majority of the vertices, they're not leaky. Let's pretend for a second that every single vertex is not leaky. Okay, therefore, like you reach these destinations V1 through V5. And if you perform a whole bunch of random walks from V1 to V5, they will like not spread because the vertices are not leaky. And so therefore, these random walks will be sitting inside a tiny ball around all of these destinations. And you can just run some proper minor finding procedure on these tiny balls and see if like any of these balls contain a minor. If they do, you just reject the instance. Okay. And if you do not find a minor like this way, like if the instance indeed happens to be a leaky instance, then you do the following, that you just try to like use the Birde paradox analysis that we presented earlier. You try to perform like a whole bunch of random walks and you try to see if these random walks allow you to connect all the terminals. Okay. We call the first phase of our algorithm the local search phase. The latter phase of our algorithm is called the find path phase, and like similar ideas were already present in papers by Kleinberg and Rubenfeld back in 1996, where they were not interested in sublinear time algorithms for this problem, but nevertheless they showed like you can find minors inside expanders like using similar arguments. Okay, so like that's essentially like pretty much like all I had to say about the one-sided variant. And now I can move on to the two-sided variant, but I would like to like check if there are any questions. So going once, going twice, and okay, going thrice. So let's move on. So like, well, what about the two-sided variant? So instinctively, you should think that, hey, the one-sided variant should imply the two-sided variant. It's perhaps just a question of managing the query bound, but like that's your intuition anyway. So let's just like try to make this like instinct precise. So remember, I mean, like we showed the following, that if your graph has truckloads of leaky vertices, so the word leaky is missing here. If your graph has lots of leaky vertices, then your graph cannot possibly be planar. Let's take the contrapositive of this statement. The contrapositive would say the following, that if your graph is planar, it cannot have too many leaky vertices. It can have at most n over L leaky vertices. Let's just record this properly. If your graph is planar, it cannot have too many leaky vertices. This is great, because now what I can do is that I will still run the non-leaky phase of my algorithm. The leaky phase, I can just get rid of it. I can just estimate the number of leaky vertices. Okay, that's all I need to do, and like game over, right? Unfortunately, like that's not quite enough, because then there is this annoying problem that our analysis could show that you have very few leaky vertices only when the walk length was kind of large, when the walk length was n to the 0.01. But this time around, I am allowed a query budget of mere poly in 1 over epsilon, like no dependence on n. So I have to like show that you have very few leaky vertices when the walk length is super small. Okay. Turns out you can still do this. And in order to do this, you exploit some deeper planar properties that I will tell you about in a minute. Like the deeper planar property that I will talk about has a name. It's called hyperfiniteness. It essentially tells you the following. It tells you that you can break the vertex set of your graph into very tiny pieces of size 1 over epsilon square. And you will have very few edges running between these pieces, merely epsilon fraction. Okay. And essentially what you can show is that if you pick some start vertex S inside this piece, if you pick some start vertex inside this piece, the size of this piece is fairly small. If the random walk never truly leaves its home copy, if you could show this, then essentially you know that the 2 norm squared of such a walk would necessarily be large. It would be at least like the reciprocal of the size of the piece. It would be at least 1 over S. Right? If the walk never leaves this piece, this guarantee would hold. And essentially you can show this. Okay. So you can indeed confirm that even for like walk lengths being super small, polynomial n over epsilon, the number of leaky vertices your graph has is very small. Okay, and like that lets you finish the two-sided variant as well. Okay. And now I can go inside the second part of the talk. And if you have any questions, do let me know. Otherwise I'm going to carry over to the second part. So I'd like to tell you like how random walks led to a very interesting primitive called the partition oracle primitive. So like, let me tell you about that slowly. And I will also tell you about the deeper planar properties I was telling you about earlier, this hyperfiniteness thingy. Okay. So it turns out that for planar graphs, which do not necessarily have a bounded degree, like something very interesting holds, that for every single planar graph, what you can show, not necessarily bounded degree, there is a set of root n vertices such that if you have to cleverly delete this set of like size merely root n, all connected components of your graph, their size becomes at most 2n over 3. The graph does not contain like some component which has connected component whose size exceeds 2n over 3. Okay. For bounded degree graphs, which we are interested in, like number of vertices, number of edges, same thing. So what I'm essentially telling you is that if you delete big O of root n edges, which you choose cleverly, you can break the vertex set of your graph into connected components whose size is at most 2n over 3. Okay, this is a so-called balance separator theorem, which was shown by Lipton and Tarjan back in 1970s. And if you work on algorithmic problems in graph theory, this should be your go-to weapon of choice, because this facilitates divide and conquer approaches to a whole bunch of like planar graph problems. Okay, and it's a heavily used technique. So what you can also show is that if you were to hit your graph with the balance separator theorem over and over again, you would be able to decompose the vertex set of your graph into very small pieces of size at most epsilon to the -2, 1 over epsilon squared. And the number of edges that will run between these pieces will be very small, like very few edges run between these pieces. At most epsilon fraction of edges run between these pieces. Okay, so like this is like a remarkable result. I mean, like you cannot show this like for every single graph. Your graph has to be a bounded degree planar graph, and such a decomposition is called a hyperfinite decomposition. It's not a unique decomposition, and they are obtained by using the planar separator theorem over and over again recursively. Okay, and like such decompositions were like first discovered by Alon, Semer, and Thomas back in '94. And they were used for making progress on algorithmic problems in planar graphs by Benjamin, Straven, Shapira, and Alec. And there are other works also that use this. But like these are the problems that were like most relevant for today's talk. And the reason you should care about hyperfinite decompositions is because they help you get good approximation algorithms for a whole bunch of graph parameters on planar graphs. So for example, if you want to get a good approximation to, let's say, the max independent set on planar graph, you can first compute the hyperfinite decomposition, and then like you can just like use some randomized algorithms to find the max independent set in a brute force way on like a whole bunch of these pieces, and you can then just scale back the answer. Okay, so like now what I would like to tell you is I'd like to tell you about the problem that I consider in this second part. So I want you to build for me the following primitive. So you would be given some vertex V. Okay. And I want you to find for me the hyperfinite piece containing this vertex, this red piece. Okay. The thing to keep in mind is that the hyperfinite decomposition is not necessarily unique. Okay. So you have to give me access to pieces with respect to some fixed hyperfinite decomposition that your algorithm should fix implicitly. Okay, there is a global hyperfinite decomposition that you do not know. Okay, and your algorithm is supposed to be consistent with some hyperfinite decomposition. And like turns out that you have to define some notion of pre-processing, using which like I can give you access consistently to the same hyperfinite decomposition. Like that I will not tell you more about. Like essentially at this point, the only thing that I want to tell you is that like this consistent tool, this hyperfinite decomposition tool, this tool that gives you oracle access to pieces of some hyperfinite decomposition, like it was built by Hasidim, Keller, Nguyen, and Norak back in 2010. And Levy and Ron refined their techniques and like their running time, the tool by Levy and Ron, like their running time was the polynomial in 1 over epsilon. Like what I did in joint works with Seshadhri-Stolman is that we gave implementations for partition oracle that run in time polynomial in 1 over epsilon. And we showed that like it has lots of applications in graph property testing. Namely, you could test every single property of planar graphs in a mere query budget of exponential and 1 over epsilon squared that we showed in Soda 22, that every single planar property, including the undecidable ones, okay, you could test them with a mere query budget of exponential and 1 over epsilon squared. We also showed that this result is tight. Okay. And now I can finish up with some open problems. So I'll first show you like some like very concrete open problems, and then I will do some fuzzier ones, like which are not too fuzzy, by the way. So a few concrete problems. So like here are like two problems that like look like myriad sitting ducks for our techniques. So like based off of our like Soda 22 paper, it shows that every single planar property can be tested in a query budget of exponential 1 over epsilon squared. Nevertheless, it turns out that there are a whole bunch of interesting graph properties that can be tested in a query budget of mere polynomial and 1 over epsilon. But there is this very annoying property, planar Hamiltonicity, that we do not know how to test. And like the reason Hamiltonicity is interesting is because Hamiltonicity avoids being put inside like the bucket of some huge testable bucket. So there is a bucket of testable properties, efficiently testable properties. These are the so-called monotone and additive properties. Hamiltonicity is neither monotone nor additive. And it would be interesting to see if you can like test Hamiltonicity efficiently. We believe you should be able to do this. We do not quite have a final answer, but we think it's testable in this query budget. And it would be very interesting to see if you could characterize every single planar property that can be tested in a query budget of polynomial in 1 over epsilon. We showed that every single one of them like can be tested in a query budget of exponential 1 over epsilon square. Now we want like properties characterized. We want to characterize properties that can be tested, that are testable with a query budget of polynomial in 1 over epsilon. Okay. A few more interesting open questions. So we would like to generalize testing H minor fineness for arbitrary graph H, arbitrary but fixed graph H of small size, to sparse graph with possibly unbounded degree. And this is something that I'm working on jointly with Seshadhri and Sabyasachi Basu. We have some partial progress, but close but no cigar, as they say, right? Then we would be rather curious to see if we can give something back to structural graph theory. Like if your graph is unbounded degree, for example, take the star, okay? It does not admit any hyperfinite decomposition. It's an unbounded degree planar graph. So it would be nice to see if you can like define some appropriate notion of decomposition to unbounded degree planar graphs, some appropriate notion of hyperfiniteness, which is meaningful even for unbounded degree planar graphs. And also it would be curious to see if you can have partition oracle for unbounded degree planar graphs as well. Now let me tell you about a few fuzzy open problems. So a few fuzzy open problems, like the first one that I want to tell you about that I'm rather interested in is to see if you can find in nearly linear time root and size balance separators in minor free graphs. So the existing algorithms, they either lose on the separator size bound or they lose on the running time bound. Either they are like not nearly linear or the separator size is significantly better than root n. Seems to us that our techniques might say something relevant here, but again, it's definitely not clear. It's super fuzzy. Okay. Another problem that you're interested in is this so-called planar embedding conjecture. So there is this conjecture that essentially tells you that, hey, the shortest path metric on planar graph or planar graphs embeds in L1 with constant distortion. I'll just repeat that. The shortest path metric on planar graph embeds in L1 with constant distortion, and like we do not even know how to show this for less than square root log n distortion asymptotically. So even less than square root log n distortion will be a great result. It would imply very good approximation algorithms for sparse cut on planar graphs. So again, that's a problem that I have almost zero idea about how to approach. Then a third problem that's like a huge open question in this area. So Kawarabayashi, Kobayashi, and Reed back in 2011 announced an algorithm that ran in linear time for finding forbidden minors. However, to the best of my knowledge, apparently their algorithm had a bug, and when they fixed that bug, they discovered that their algorithm had running time quadratic in the number of vertices. And it would be super good to see if you can get subquadratic algorithms for this problem. And finally, it would be good to see if you can have sublinear time algorithms for testing bounded expansion. If you could generalize this stuff to bounded expansion graph classes. So that's all I have. Thanks for your time.